Hi everyone, welcome to our class. Today our invited speaker is Dr. Anita Drummond. She will speak about the South Atlantic Dipole, and I invite her to present herself. Anita, please, you have the space. All the space is yours.
Okay, thank you, Michelle, for the invitation. Hi, everyone. Nice to meet you, and thank you for joining this lecture. Okay, I will try to share my screen. Let's see if I can. Oof. Okay. Whoops. Ah,
Yes.
yes.
Okay, it's working.
Thank
You
you.
can
So,
see the slide of your introduction.
okay, so I up again. Sorry, I will put in this division. I will turn off my camera because I'm not sure about the quality of the connections. Okay.
Okay, no problem.
Okay, so let's see. I can't do this now. Okay, let's see. Okay, so it's better. I feel more comfortable. Okay, again.
Yes.
Are you see it? Yes.
Perfect. We can
So,
see your slide.
cadê? Aqui.
Then,
And how can I
yeah,
how
put,
can I do this? I put here?
yeah, you can put to the corner. Yeah,
Yeah.
it's okay.
Okay. Let me see. Why? Okay. So, hi everyone. Before we start, I would like to let me introduce myself. And currently, I'm a postdoc researcher at Valley Institute of Technology. I collaborate on a project about monthly rainfall forecast. This project is supervised by Dr. Renata Tedeschi, who already gave us a lecture about ENSO, and my personal research focuses on the influence of the teleconnection modes on the climate of southeastern Brazil. About my background, I'm a meteorologist from the University of São Paulo, Brazil, and I worked as a researcher at University of Vigo, Spain, for 10 years, investigated atmospheric moisture transport through Lagrangian models. When I come back to Brazil, I worked as a visiting professor at Unifesp, and after that, I worked as a postdoc researcher at USP, where I studied extreme climate events and moisture transport over South America. I also collaborate with the climate monitoring activities developed by the Climate Studies Group from USP. And my main research interests are climate variability and extremes and atmospheric moisture transport. So here we go. Today we will talk about the South Atlantic Dipole, the mechanisms, variability, and impacts over South America. This presentation summarizes all the review done along this year with the collaboration with Renata, Nathan, and Michelle. Introducing Nathan, Nathan is here attending this lecture. He's a master student that I have the opportunity to, let me just a moment, okay, to co-supervise with Michelle, and he's studying the climate variability over the South Atlantic and its impacts over the South American climate. And now he's preparing a paper with his results. This presentation is available through this link if you want to download after. But okay, here is the outline of the presentation. We will start reviewing the South Atlantic climate background. Then we will introduce the South Atlantic dipole, hereafter the SAD. We will see the evolution of the scientific understanding. We will examine the physical mechanisms behind the SAD. We'll talk about the seasonal variations of the SAD and the indices used to measure the SAD. We will analyze the impacts of the SAD on the South American climate and how SAD interacts with other climate modes. We'll talk a little bit about the major climate change effects on SAD, as well as the model representation and the futures projections. And at the end, the final remarks. So let's start reviewing what we learned from the previous lectures. We learned that teleconnections link distant regions. And we also learned about the role of the oceans in climate variability, such as NCPDO and Pacific, SAM in the Southern Hemisphere, the AMO and TED in the North and Tropical Atlantic, the IOD in the Indian, and all of these patterns, these climate patterns, can affect the South American climate in different ways. But now, what about the South Atlantic Ocean? Is there a variability mode that can influence the climate in the surrounding regions? This is what we will explore today. So, let's start reviewing the main South Atlantic climatological features. We will start with SASH, the South Atlantic Subtropical High. It's a large, semi-permanent high-pressure system located over the South Atlantic. It's connected with the trade winds, which flow from southwest towards the equator. And they are very important to drive the oceanic currents, the upwelling at the African coast, and the SST distribution. The SASH changes, the intensity and the location of SASH changes along the year. During the summer, it gets weaker and displaces southward, and during the winter, it gets stronger and displaces northward. In the South American, there is an important feature connected to SASH, that is the South Atlantic Convergence Zone. We learned a lot about it in the Marciazielis lecture, but remember, it rolls on the summer rainfall in the tropical subtropical South America linked to the SAMS, the South Atlantic Monsoon System. In the ocean, there is the South Atlantic gyro, which is formed by warm and cold currents that connects the tropics with the extratropics. At the Brazilian coast, there is the Brazil current, bringing warm waters southward, and when it reaches around 35 degrees south, it meets with the Malvinas current, a cold current. So this region is known as the Brazil-Malvinas Confluence Zone and is known by presenting a strong temperature gradient. From this region, the South Atlantic current flows eastward, and when it reaches Africa, it turns north as the Benguela current, carrying cold waters towards the equator. And when it reaches the equator, it turns left as the South Equatorial current. So the South Atlantic gyro is connected with the SASH, the South Atlantic Subtropical High, and this system is very important to modulate the South Atlantic variability, as we'll see later. Okay, so what is the South Atlantic dipole, the SAD? The SAD is the dominant mode of coupled atmosphere-ocean variability over the South Atlantic. It's characterized by a northeast-southwest dipole pattern with centers of action over the tropical and the extratropical South Atlantic. It can present variability on intraseasonal, interannual, and interdecadal timescales. Why studying the sad make us feel so sad sometimes? I'm trying to make a joke in English, but it's because its investigation still faces many challenges. First of them, there were few in situ observations over the South Atlantic before the 80s. 80s is the onset of the satellite era. In order to illustrate this issue, this map shows the number of observations uh, assimilated by the ERA 5 reanalysis from 40s to the current days for different variables. And let's focus on the surface pressure, which is one important variable to characterize the set. Keep in mind that cool colors means a low number of observations, while the warm colors means a high number of observations. If we focus on the South Atlantic, we can see orange colors only after the 80s afterwards. So if you want to study a long-term climate variability in South Atlantic, there is this problem of the lack of data before the 80s. Okay, another issue is that, as far as we know, the impacts of SAD are very regional. They are mainly limited to South America and Africa. That's maybe is one reason for the SAD receives less attention when compared to ENSO or the Indian Ocean dipole, that are climate phenomena with known impacts at global scale. And a very important issue is that even when we study the SAD, the results are very dependent on the data, the domain, the time period, and the statistical methods used. We discuss this later. But anyway, beyond all these challenges, the SAD still offers many opportunities for new research. So, how has the SAD been discovered and studied over time? Let's start with my personal experience. The moment the South Atlantic first caught my eye was in 2001 during a very big energy crisis in Brazil. That was a weak La Nina, maybe a Modoc year. And so in La Nina years, we expected more rain in Brazil, in the SAMs. However, it was very dry, as we can see from these clear gray colors in the 2001 summer precipitation anomalies. When you look at the SST, we can identify in the South Atlantic a dipole pattern. However, at that time, no one talked about the SAD, and I didn't know it neither. And actually, we are not sure if this particular signal is related to SAD. But anyway, this case study was the motivation for my PhD that tried to link this South Atlantic pattern to Tedroff in Brazil. However, when I run an atmospheric GCM model forced by this dipole, the experiment was not able to reproduce the continental pattern, continental rainfall pattern in the South Atlantic, in the South America, suggesting that the atmosphere might be driving the ocean. If you want to know this work, there is the reference at the end of this presentation. But anyway, since then, the South Atlantic never left my mind. Okay, so a brief history. In the late 90s, the first works identified a dipole in the South Atlantic, and Venegas et al. Used the EOF and SVD statistical analysis, and they found a couple SST dipole and a sea level pressure, SLP, linked to shifts in the South Atlantic subtropical high, the SAD. However, these first works brought some methodological challenges because these statistical-based analyses are very sensitive to pre-processing choices, domain, and analysis period. So, different authors sometimes found different results, what leads to controversies. After around 2010s, the concepts involved SAD become clear. Morioka et al. In 2011 found the SST dipole as the first EOF mode. They denominated SEST with a summer peak. Nanch et al. At the same year found the dipole as the second EOF, denominated SAD with a winter peak. Later, some years later, Nanch et al. Found that both results represent the same physical mode. Later studies such as Caiano, Bombard et al. Here, Bombard, I put in red because it's only an example of all the work developed by Professor Leila Carvalho's group in order to understand the South Atlantic variability. And that is the recent work of Peer. All of them identified the dipole as the leading SST-SLP couple mode, the SAD. And it's interesting that Caiano also identified other climate variability modes in the South Atlantic. Okay, let's talk about the physical process behind the SAD. The major is that the atmosphere-ocean coupling related with the SASH variability. So any change in the strength or position of the SASH will modify the surface winds and heat fluxes, which influence the SST across all the basin. This map represents the first SVD mode obtained with SST and SLP. It was obtained by Venegas et al. And we can interpret these patterns as the anomalous patterns observed during a SAD event. So this structure is representative of a negative SAD phase. That in terms of SST, it presents cold water in the tropics, warmer waters in the subtropics. And in terms of pressure, there is an increase of sea level pressure across the basin associated with a stronger SASH. In the positive phase, it occurs the opposite. So, warmer waters in the tropics, cold water in the subtropics, and low sea level pressures associated with a weaker SASH. As we see before, different authors may propose different processes to explain the SAD evolution. Here, we'll see the processes for the SAD evolution according to the Morioka et al. Theory. Remember that for them, SAD peaks on summer. So it starts to develop in the late spring. According to them, the major driver is the atmosphere, especially variations in the South Atlantic subtropical high. So imagine this scenario of a development of a negative SAD event with peak in the summer. So in the late spring, a southward shift and intensification of the SASH will change the surface winds, affecting evaporation and latent heat flux. So where the winds becomes stronger than the climatology, the evaporation and the latent heat loss will increase. And where the winds become weaker than the climatology, the evaporation and latent heat loss will reduce. These strong winds also increase the turbulence and deepen the mixed layer, reducing the short wave heat inefficiency. So, these three processes together will reinforce the negative SST anomalies. On the other hand, the weaker winds will reduce the turbulence and show the mixed layer, so increasing the short wave heat inefficiency. And these three processes together will reinforce the positive SST anomalies. According to them, the SAD decay following the climatological seasonal cycle. So, from summer to late autumn, climatologically, the mixed layer deepens as the climatological winds strengthen and the solar heating weakens in the south hemisphere. So this deepening of the mixed layer is associated with the entrainment of cooler subsurface water, which damps the SST anomalies. In the late autumn, the stronger climatological winds will increase the latent heat loss, enhance the surface cooling. So both entrainment and latent flux will contribute to the decay of the SAD pattern. Net et al. Explained the SAD evolution through a process that peak in winter, also showing a couple atmosphere ocean. In the recent work of Manta et al. Showed that the SAD can be shaped by both atmospheric and oceanic variability, and their relative influence will change according to the time scale of the oscillations. So the final message is the SAD is complex and there is more than a way to interpret its physical drivers. The SAD presents seasonal variations expressed through two main variants. First, the South Atlantic subtropical dipole, the SAST, defined by Morioka et al., that peaks in austral summer when the sashes shift southward. Then, this is confined to subtropical latitudes. The second variant is the South Atlantic Ocean Dipole, the SAD. It was defined by Nutch et al. It peaks in austral winter when sash shifts northwards, so it extends across broader latitudes. So based on these two variants, two main indices were developed to monitor SAD, and they were based on SST anomaly differences between two regions. For many authors, SAD is defined as the difference between the northern and the southwestern pole. So a positive SAD will be associated with warmer northeast pole and cooler southwestern pole. But this definition can change depending on the author. It's important to have in mind that the index choice may affect the results. I will explain why. Okay, let's go for the first index, the South Atlantic Ocean Dipole Index, SAD, proposed by Nash, and it's represented by these red boxes. And we can see through this position that it captures equatorial influence. The second index is the South Atlantic Subtropical Dipole Index, known as SASD, proposed by Morioka, and represented by the green boxes. According to their positions, we can see that it focuses on the subtropical variability. It's important to note that the SAOD's northern pole overlaps the Atlantic Neon region, and the SAS's south pole is fully inside the SAOD southern pole. When we work with indices, it's important to know their strengths and limitations. For our case, the strengths are that they are both of them are simple and widely used for monitoring SAD variability. And both of them capture the SST dipole pattern. But we need to be aware of the limitations. The first of, both are very sensitive to box definitions, so any small shift can change the index values. Another is that SAOD partly overlaps with the Atlantic Neon region, remember. And this can mix the signals of different phenomena, climate phenomena. Both of them are dependent only from SST, so the indices do not separate atmosphere-ocean couple mechanisms. And in my opinion, the most serious is that they cannot represent the spatial shifts. Oh, that means the latitudinal migration of SAD. Remember that the SAD changes its position along the year and along the decades, as we will see in the climate change results. In how do you define extreme SAD event? They are commonly defined when the index exceed plus or minus one standard deviation from their climatological mean. This is the methodology that we use to identify extreme events for a lot of climate phenomena. And if you want to know them better, to study or to monitoring them, these index are available, are openly provided by the Teleconnection Index Online tool, provided by the Federal University of Itajubá through this website, and the paper is on review. In this web page, you can find the monitoring of different climate phenomena. So now I suggest you to visit it. So let's go for the next question. How does the SAD relate with the South American climate? Bombard and Carvalho studied the relationship between SAD and the SAMS. And they found that the SAD is associated with a dipole in rainfall between the northeast and southeastern Brazil. They found that during a negative SAD event, that is characterized by a cool northern pole and warm southern pole, it's associated with a stronger SAD, remember. So in this scenario, the wet season in the SAMS, the South American monsoon season, it starts earlier, it's longer, and wetter brings more rain. And on the other hand, the wet season in northeastern Brazil starts later, is shorter and drier. For a positive SAD scenario, characterized by warm North Pole, cool Southern Pole, and weaker SASH, the wet season in the SAMs start later, is shorter and drier, while the rainy season in northeastern Brazil start earlier, is longer and wetter. Ireland to bombard at all, a Rossby wavy trend from the extratropical Pacific helps to trigger the circulation anomalies in the South Atlantic. Let's consider the negative SAD scenario. If you look at the moisture flux anomalies associated with the intensification, with the intensification of the SASH, there is a cyclonic anomaly over the southeastern Brazil. This circulation helps to enhances the moisture transport from Amazon towards the subtropics, causing the intensification of the SACS, the South Atlantic Convergence Zone activity. In the opposite scenario, the positive SAD, remember that is associated with a weakened SASH and with as anticyclonic circulation over southeastern Brazil. This circulation reduces the moisture transport from Amazon towards the subtropics and brings a weaker sex activity. It's very important to have in mind that methodological choices may shape the said precipitation relationships. For example, we know that SAOD has a low skew in summer due to the weak North Pole SST signal. So any analysis based on SAOD may present low impact during the summer. Remember, SAOD is the variant found by Nudge. So when Reboit et al. Studied the SAOD through composites, they found that negative SAOD is associated with wetter conditions in North and South America only during winter and spring, when is the peak phase of the SAOD. And later, Carpenedo and Silva analyzed the SAOD using linear correlations, and they found that a negative SAOD is associated with wetter conditions in southern Brazil and Cerrado, and drier conditions in northern Brazil for all the seasons, but except for summer. Let's go for the next question. How does the SAD interact with other climate modes? We know that the SAD often occurs with other dipole patterns in the South Hemisphere, like the SIOD, the South Indian Ocean dipole, and the South Pacific dipole, mainly in austral summer. And these dipoles are influenced by large-scale atmospheric wave pattern in Southern Hemisphere circulation, known as the zonal wave number 3 or 4. And these wave patterns will modify the subtropical anticyclones, then triggering the dipoles. It's known that the SAD interacts with ANSO, AAO, AAMO, and PDO on internal to decadal time scales. But let's focus on the ANSO-SAD interactions. It's interesting that the strength of the connection depends on the timing and type of each event. So the ANSO-SAD link is not stationary. It changes with time. But in austral summer, ANSO affects SAD mainly via the PSA wave trend, which modifies the SASH. And for the current climate, during El Nino and positive SAD scenario, Both of them will contribute for a strong wet season in southeastern Brazil. And during La Nina, a negative SAD event will also contribute for a strong wet season in southeastern Brazil. This relationship is stronger in lagged correlation, especially with the Central Pacific, not Eastern Pacific, with the Central Pacific El Nino events. And the relationship is two-way. Anson can lead SAD, and that SAD can also lead Anson. The Anson-SAD relationship changes on decadal scales. And this ASO and SAD coupling is strengthened in recent decades due to shifts in the ASO regimes and phase reversals of the decadal variability modes around the turn of the century. Remember that IPO covers all the Pacific Ocean. It's different from the PDO that affects only the North Pacific. So a positive phase of the IPO that's similar to El Nino, but in low frequency, favors negative SAD during El Nino on interdecadal scales. In AMO also modulate the Anson region. A warm AMO brings more Central Pacific El Nino that is strongly related with SAD. On the other hand, cold AMO brings more Eastern Pacific El Nino. So, knowing this, the Anson-SAD correlations are stronger during warm AMO phases, what we have been observing in the last years, and weaker during the cold phase, what was observed at the end of the last century. So, how does the climate change affect the SAD? We know that the climate change is reorganizing the large-scale circulation in the last decades. So, it affects the ASO regime and teleconnections, altering the ASO-SAD relationship. And the climate change is also affecting the long-term changes in the SASH. There is a SASH expansion during the summer that will influence a southward shift of the dipole and of the South Atlantic convergence zone. And about modeling the SAD in the SEMI-6 models, let's review two recent works. Here, this slide summarizes the results found by Beer. And concerning the historical period, he found that the models, these particular modes, capture the basic SAD features, especially on pattern, oscillation period, and seasonality. However, they failed to represent the Atlantic Nino signal that is typically coupled to the SAD. And in addition, they do not reproduce the southward shift of SAD in recent decades. So, according to him, the models may underestimate some RC couple process in the tropical South Atlantic. About the future, he found that these three models project a stronger SST, SLP, and precipitation anomalies, especially under high emission scenarios. And SAD remains linked to this dipole dryfall pattern between the northern and southeastern South America, with an intensification of extreme events. In another work of Umbergo and et al., they found that the models show limited skill in representing SAOD. SAOD is the Nancy mode. Rainfall impacts over southeastern Brazil during Austrian winter. They also found that the divergent future projections of the SAOD rainfall relationship under high emission scenarios, what highlights large uncertainties for countries affected by SAOD variability, that are South American and African countries. So let's conclude and summarize what we learned from this lecture. SAD is associated with a present-day South American climate. Sex behavior, Amazon southeastern Brazil moisture transport, and rainfall dipole between northeastern and southeastern Brazil. The mechanisms involve such intensity position change, which winds affect evaporation, surface heat fluxes, and mixed layer depth variability. Draws wave trends from the Pacific and wave number 3 or 4 pattern can also trigger changes in SASH. SAD shows seasonal variability. NOAA says in summer or SAOD in winter. And SAD is sensitive to the index choice. ANSO, AAO, AMO, PDO, AIPO, all of them can modify the SAD behavior on interannual to decadal time scales, producing non-stationary relationships. Concerning climate change, know the influence that changes in nation regimes and teleconnections can affect the SAD, and the expansion of SASH that shifts sex and SAD southward. The SIMIP6 models reproduced the SAD basic patterns but failed to capture some of the ocean atmosphere coping and showed large uncertainty in the future SAD rainfall projections. So, some of the many key open questions concerning the long-term trends and mechanisms behind the SAD seasonality, changing the ENSO-SAD link, predictability of SAD, and role of the ocean atmospheric open, and the regional impacts in the South America and Africa. So, thank you a lot for your attention, and at the end you can find the reference used to this presentation.
Thanks a lot, Anita. I stopped the recording.
Let me try to